Schönen guten Abend, meine Damen und Herren. Herzlich willkommen zu unserem heutigen MIRACUM DIFUTURE Kolloquiumsbeitrag. Nachdem wir uns in der letzten Woche mit Bildern aus der Pathologie auseinandergesetzt haben, werden wir heute wahrscheinlich ein bisschen die Modalitäten wechseln, aber wir bleiben im Bereich der Bildgebung. Und es geht um die Erstellung multimodaler Datensätze für föderiertes Lernen mit DICOM-strukturierten Berichten. Unsere heutigen Vortragenden sind Herr Malte Tölle und Sandy Engelhardt, beide aus der Klinik für Kardiologie, Angiologie und Pneumologie am Uniklinikum in Heidelberg. Und ich freue mich auf Ihren Vortrag. Bitte schön.
Dankeschön. Herr Tölle wird jetzt gerade die Folien teilen. And then we would switch to English if this is fine.
All right, thank you. Yes.
All right, then I would start. Thank you for the invitation. Sandy and I will present today our project on dataset creation for federated learning in healthcare, a multimodal approach to imaging, ECG, and metadata with DICOM. I would start by introducing the use case for which we motivated our consortia and which we applied the federated learning procedure, and that is the transcatheter aortic valve implantation, or TAVI for short. TAVI is a replacement of the stenosed aortic valve in a minimally invasive way, which leads to less trauma after the operation, but the problem is that the prosthesis exerts additional pressure on the heart conduction system, so these patients have a higher risk of receiving a permanent pacemaker after the implantation. So our goal is to quantify the risk that a patient has for receiving a pacemaker for a specific prosthesis after TAVI, and by that make the perfect or a good selection of a prosthesis for a patient. Problem number one is that we have many modalities, many examinations, many, in our case, retrospective data that is important and has information regarding our endpoint of whether this patient needs a pacemaker after TAVI or not. That is, of course, the implanted TAVI prosthesis, and then we can get measures from the CT image. We have information regarding already existing conduction abnormalities in the ECG. Further, some information is in the billing data and also in the quality assurance data, which is mandatory to document in each case. Problem now is that we have different time points of the different examinations and when the data is recorded. And also we have completely different formats across the hospitals. For the CTs, it's rather standardized in forms of data type. It's all DICOM, but finding the right CT series to use is difficult across locations because they all have different naming conventions regarding study descriptions or series description, etc. In ECG, for ECGs, it's more difficult. We have different formats in hospitals, even intra-hospital wise. Sometimes we have different formats of the ECG, which range from ECP ECGs over DICOM and XML, and we needed custom scripts for all of that, and custom matching, of course, would need. Further, as said, the quality assurance and prosthesis data, they're at least all in Excel or CSV format exportable from the clinical information systems, but we also have different naming conventions here, which complicated the process of creating matched data and the same data cohorts with the same filtering ability across all locations. For example, we needed always the last ECG before TAVI in the same format across all locations. Why do we need the multi-center approach in our case? Why is that needed? When we look at the literature, at the studies who quantified factors that are important for whether a patient needs a pacemaker after TAVI, and we didn't look at the factors at first, we only looked at the reported pacemaker rates in their single center studies, which you can see on the y-axis here, x-axis is here, and color is the type of prosthesis used, which is not that important. Important is that they all report different rates, even for the same prosthesis in the same year, which means there are definitely center-specific factors at play, which we wanted to eliminate in our multi-center approach. Problem for us was that because of privacy constraints, the data was not allowed to leave the individual hospital boundaries. So we needed to use another training procedure, for which we chose federated learning, where the data stays within each hospital. It's not seeable from other people from the outside, and we only send the model around, train individual in each location, and then perform some form of averaging on the server, only of the model weights. We established a consortia across 8 university clinics in Germany, which all contributed data to our use case in different quantities and also different data types, but more on that later. We have established a consortia in which we also would like to use, or which is planned to use for other use cases in the future after the TAVI use case. We installed the same network, the same architecture, the same infrastructure in each clinic, where we built upon the developments from Kapana, which is also used in the MIRACUM project, and in NUM, where we used the Kapana platform for container orchestration, and such that each hospital has the same PAX infrastructure and the same Docker environment to start individual containers within Kapana. Then, for the actual federated learning process, we used FedBiomid, which has I would say, about the best security guarantees for medical applications. They have transport layer security, so encryption in place, but also algorithmic security in form of differential privacy or secure multi-party communication, which one does not have to worry about then from as a data scientist or as the data owner, the hospital, that data is leaked in some form, either during communication or during computation. We also developed a dashboard with which we could investigate training from remote as a data scientist. When you start the training, we have additional information here, such as an error that occurs at location, at one location. We can investigate, and by that make the troubleshooting faster to enable better training. There was a learning that we had that this is very beneficial for training. All right. Having talked about our infrastructure and our consortia, how we established that and what we have used for that, I will now come to the actual use case and how we created the data sets that must be homogeneous in type and structure across locations. For the final use case of predicting whether a patient, or the risk of a patient to receive a pacemaker after TAVI, we had a quite complicated query on each individual data source, which of course started with the inclusion criterion of the patient needed to have a TAVI. It must have a CT. Then we needed the specific CT with contrast agent, and it has the patient has an ECG recorded before TAVI. Further, we had some exclusion criteria, for example, that the patient was not or should not have a pacemaker before TAVI. We cannot quantify then whether he or she gets a pacemaker afterwards because of TAVI or because there were already pre-existing conduction abnormalities, and it shouldn't be the second or third TAVI procedure. The most important part here is that all of these different information come from different information systems within the hospital. For example, the CT is in the PACS, the ECG comes from the ECG machine mostly. We have the quality assurance data and the billing system from the material system, and we need to filter each data type or each query has linkages to other ones here. So we thought, to be sure that each location has the same dataset structure and type, we need to convert all data to a unified format first, such that we can query all in one place. and make sure that this matching is always done in the same way. And we chose DICOM for that because as we started, and our study is very imaging focused with the CTs, and also the ECGs are at least partly already in DICOM. We investigated and came to the conclusion that converting everything to DICOM would be the best way for us. So each hospital exports the data they have in the format they have. Then we convert everything to DICOM. Make sure that we, of course, match it on the patient ID wise, such that we can make use of DICOM's intrinsic matching capabilities. We upload it into a PACS, which is there in Kapana and standard in every hospital. And then we have it in a database and could build a graphical user interface for filtering on top of this, which again makes use of the inherent capabilities. We can make a query in one hospital, copy that query and send it to other locations to get to the exact same cohort with their respective data. As said, why did we choose DICOM? As said, we were a very imaging heavy study, so we thought we can at least reduce complexity a bit by sticking to this format. And as also said, it's a well-established standard, and every hospital and also Kapana has the storage infrastructure already in place, and there was no further work to be done here. Further, we can cross-reference on different levels, which I will also show later, with the metadata and the different modalities, and there exist open source viewers for images and ECGs, and also the structured reports can be displayed. Now, I introduced the term of structured reports, which we used to store the metadata, which we have additional to the images and ECGs, which is a rather old format in DICOM, so it was introduced a few years back, but now the library HiDICOM has made use of it in Python object-oriented ways, such that it can be used in Python deep learning frameworks and workflows, such that it's easily handleable in Python. And we could then also in Python convert all our data into these structured reports, which are standard ways to store the clinical findings and also quantification of these findings, as well as localization results in predefined templates. There already exist a multitude of these templates for various different use cases. For example, here there is a template for cardiovascular patient characteristics. An ECG report is there. CT and MR analysis reports. So almost all information is possible to be stored in these structured reports and then matched with other DICOM objects on different levels, which is shown here. For example, when we have a CT image and we have a segmentation of that images with different segments, here you see segments of the heart, and then this image also has a structured report. We can also reference the measurement that is made on the segmentation of the aorta within the existing DICOM standard, and this means we can also query it on that level. And of course, the same holds true for the ECG as well. We then extended the HiDICOM library, which was mostly imaging focused, with templates that we implemented in DICOM in Python, from which you have seen two slides back, such that we could make use of them in Python deep learning library. For example, here in Python deep learning workflows, for example, here you can see the cardiovascular patient history, and we have also open sourced this code in our GitHub repository, such that also others now can store their data in these DICOM structured report templates. This is how it looks like if one then creates a structured report. One can reference, for example, the ECG Python object here and store it in the report, and also create pressures or other measurements which can be stored in the report in, as said, a Pythonic object-oriented way. Where we have also, this is an example structured report, which we have also published in our GitHub repository from that publication. This was how we created the structured reports in Python, and then we had DICOM objects and could store it in a PUX. Here you now see how we then developed the dashboard with which we could query this data in an interlinked way and in an intuitive way, such that also people who are not familiar with how to do this in code could create these queries and also visualize directly how their cohort, how their data set structure is. And we used, again, of course, Kapana at each location, and then used OpenSearch to create this dashboard, which is based on JSON and where you have highly customizable options to creating these plots, which you can see on the right and also in action here. And with this, I would hand over to Sandy for the second part.
Excellent. Thank you, Malte. So here you see the created dashboard, which runs in all hospitals. And basically the use case is we want to define our query on our data. So we want to filter our data with respect to certain criteria. For example, we want to restrict the age range of the patients we want to analyze, or we want to find all CTs that have a certain annotation or segmentation. And with this graphical user interface, we can basically define such a complex query. And this query is then sent to the other hospitals that we also have in the other hospitals the same subset of patients where we want to train on. And I think it's quite intuitive to use. And you see also linked views. So if you change something in one plot, all the other plots are adjusted. Okay, next slide. In terms of like coming a little bit back to our use case of defining pacemaker dependency after TAVI, you see here a little bit of an overview on how many different heterogeneous data we actually integrated. So, for example, we have in blue here the CT data sets we have in each of the hospitals, but then we have different amounts of annotations that were derived from these CT data sets. For example, specific landmarks that define the aortic valve or specific distances you can measure in the heart that are important to define whether this is a good prosthesis for this patient or whether we can maybe expect some problems in terms of the conduction system of the heart. Yeah, and exactly then we have different amounts of these kind of data sets. You see another plot here in color. Color represents all the different hospitals. And then below the bar, you see some of the data types described and also linked data types. And you see, for example, all of the hospitals have a CT and have different amounts of CT. But if you, for example, look at the calcification column, you can see that not all of the hospitals have annotation of calcification. And this made training of a neural network approach very, very difficult because we had different amounts of annotations for different data sets. And maybe you can go to the next slide. I will come back to this in a minute. So federated learning in this case enabled us a very interesting way of defining our test cohort and our training cohort. In single center training, you usually have only one single center, and sometimes you only train and test in the single center. In our infrastructure, you can then test on the other remaining clients, which is an interesting configuration because you can see how big is your generalization gap. But this is only one approach how you can use such an infrastructure. You can, of course, also go for federated training, which we have done because we have not so many patients in each hospital, so we need to combine data sets to actually come to good results, and I will show the results at the end of the talk. So here you can see, for example, we used some of the clients for training and some of the clients for testing. Yeah, and here you can see some of the results we have. This is a CT data set, and on the CT data set, we can, for example, quantify different landmarks, for example, the hinge points of the aortic valve, or the amount of calcification at the valve, or the membranous septum length. This is all done within one network architecture. And what was especially challenging, as I already said, we learned across partially labeled clients, and we used many unlabeled data that can improve the performance. And you can see, for example, on the right-hand side, we have many different amounts of CT images. For example, here in one location, we have more than 3,000. In another location at L8, we only had 26. So this is a significant difference, right? And on top of that, we had very partial annotations, for example, of the membranous septum. In one location, we had labels provided by an expert of 73 patients in total. In other locations, we had 0. In other locations, we had 20. And this complicates network training, as you can imagine. But Malte came up with a very good solution to fix this. And maybe you can show the next slide. We do not want to go into detail because that's not so much the focus of this talk. We are more focusing here on the data set integration, not so much on the actual network architecture. So if you are interested in feel free to look into the paper. But basically what we've done, we used knowledge distillation to distill knowledge from 3 different units into a single transformer architecture, and this helped us to deal with the situation, and we could gain the same performance with this multitask network than having trained single units for single tasks, which we found is a very exciting solution to the problems we think other major and big consortia will also face when it comes to dealing with clinical relevant questions. Okay, so now we are coming almost to the end. What we've done was not only looking at analysis of the CT images, but we actually integrated other modalities like the ECG, as already said, and this is now combined into one network architecture or one machine learning approach, federated machine learning approach that allows us to quantify whether a patient will receive a pacemaker or not. And here you see the first results. These are preliminary results, but it gives you already quite a good insight what happens when you go in a federated way. So here L stands for the single locations, and in each plot you see how single training works well on the cohort where the network was actually trained, but it almost completely fails on all the other clients. So there is a big generalization gap. But in the federated case that is just shown, you see that the performance does not drop so much. So we have a much better or much more robust approach, which can, which has a better average performance over many different clients and many different cohorts and hospitals. With that said, I'm coming to the end. So what we've shown you was a successful demonstration of a real-world federated learning use case installed in 8 hospitals throughout Germany. We've shown that you can use existing standards for cross-institutional training and, of course, first making data sets more homogeneous. We found that coming more from an image perspective, that DICOM is already a well-established standard, and we wanted to leverage that. Of course, we are aware that there are other standards in the field like FHIR and other major consortia using these, but we want to make you aware that We also included some conversion scripts between DICOM standard reports and the FIRE format. For example, you can find these examples here in the provided links. And with that, I'm coming to the end of the talk. I hope you have some questions for us, and hopefully we could give you some inspiration how to use such kind of libraries or interlink these libraries for your own research projects. Thank you very much.
Thank you very much also for the very nice and interesting presentation to both of you. Are there questions from the audience? I assume there should be some. No direct question yet. So let me start. You have explained the mapping and the harmonizing of the data set in a very straightforward way. Typically, it's just a very complicated process, probably not just a week sitting together and doing this, but more work of 1 or 2 years. Can you maybe explore a little bit more how in a consortia of 8 hospitals and over time, how the work was arranged to really harmonize those data sets with all the different modalities and data types to be harmonized?
Of course, that was a very long procedure, and it took us quite a long time until we had it. So we had different data types and different formats in each location, and then the advantage of having DICOM and also the templates for the structured reports is that your final format is fixed. So you know in what you have to convert, and this is kind of at least a little error proof. Yeah, and then we started to write these conversion scripts, and for some locations you need to do it very individual. You then also gained a little bit of experience. A few locations had it quite similar, and then you could at least use the same scripts again. But yeah, that was definitely quite some effort, and it took a long time, but finally our way, we believe it worked. Yes.
Typically, you wanted to add something, Sandy?
We started around 2021, so it was quite some time, but we felt like it is very beneficial to develop such an infrastructure. I mean, we also had to install the computational infrastructure during that time. That was also not there. So it took us, we really had to start from scratch. Not only, we haven't detailed upon that yet. But yeah, it was really a long time to reach this, and it's still, we are not finished yet. We are still integrating data, but I think this is nice. So as soon as you have established it, you can still go on and continuously integrate data and answer more and more clinical relevant questions. And this is what we want to, yeah, that's what we want to do. And I think most of the federated learning consortia do not develop so strongly along a certain use case. They are a little bit more focused on the broad picture, which is also a completely understandable approach, but we had always our goal, and that helped us a lot to come to a solution.
To focus on a particular data that's needed for this use case, yes.
Yeah.
Martin Böker has a question.
Yes, thank you for your talk. I'm just on my way. I hope you can understand me well. So I wonder if there is a connection to the medical informatics initiative in your work, because we are doing quite the same in this other context. And we also have a larger project called Akribis, dealing also with ECG data. Do you have any connections to medical informatics initiative, or
Of course,
Is
here at
it
campus, we are connected to HiMate, and my colleague Christoph Dietrich is part of Akribis. Yeah, so federated learning is not a novel topic. Yeah, many people deal with it. Also, NUM, like Raccoon, is a very familiar or very big consortium. For us, it was difficult to get access to the NUM infrastructure. If you talk about NUM, many years ago, yeah. But many years ago when we started, so we had no access basically, and that's why we decided to basically start from scratch. Now, but we are still compatible because we are really using similar libraries or platforms like Kapana. And in terms of the MMI oder Medizininformatik-Initiative, I think the strongest link, of course, would be to exchange what we have done in terms of our platform. So it could easily, like our software could easily run in the data integration centers. So we are happy to provide feedback on what we have achieved. But so far we are not integrated in the medical.
Making the software available is a very nice thing to change and learn from the others. But the more complicated thing would probably to really harmonize the different types of semantic annotation and the meaning of the structures. You can always write some transformation from DICOM into FIRE, but the complexity is not just in writing a code to transform from one data structure to another, but to understand the semantic meaning of each different item. This would probably be very helpful to keep the connection to Akribis, at least while they are building up a structure for ECG data as well, so that they do not start from scratch and could take over some of your lessons learned.
Yes, of course. We are happy to share.
Yeah, and probably to private aim also because of federated learning. Probably they, I think it's quite similar.
Yeah.
Compared to what you're doing.
Yeah. I haven't seen real world federated learning yet. So I think the others are more into still development of their platforms. It's still a difference to actually train algorithms then in the federation on clinical data. Yeah, but we are happy to provide our experience of.
Yeah, I think they are about to release their software called Flame, which is based on prior work, and so probably this could be tested with your data. Would be interesting.
Yeah.
There is another question from Alexandra.
Yes, I'm not having a question. I'm also in Akribis, and I would strongly recommend maybe to make a contact. You can write to me. I can get you the contacts, or because it's such a big project, or you give me your contacts, and I'm going to hand it over to the work package in which this is done. We are just now. It starts to get interesting because we have from all the different hospital integration systems, we have got now the possibility to harmonize the data more or less. So, but this I'm not into this. So I need somebody else to explain this to you. What's going on?
Yeah, great. So the harmonization step is basically the biggest step. As soon as you have that, it's not such a big deal to run the like to run the neural networks, and so we are happy to make the link here.
But we're talking about these short ECGs, no? Not long-term ECGs or Holter or something. We have these 10-second bits to analyze. Okay.
Yes.
This is the same here. But it would be great to see what you have done. Maybe there's still something to. I think there's still something to improve or to maybe change.
Sure.
Thanks.
If I have found your contact data, Ms. Cieslak, I think you can find the contact data of Ms. Engelhardt and Mr. Töller on the website of the clinic and can contact them directly then to exchange experiences. Okay, is there any more question? I don't see anybody yet, so I would like to finish today's colloquium. Thank you very much for coming and sharing your very interesting experiences with us. We wish you good luck for all the next steps in your progress and in your project and going on with further machine learning approaches. And maybe there is a good chance for doing some cooperation on getting closer together.
Yes, hopefully. Thank you so much for the invite and have a good evening.
Have a good evening. Bye-bye.
Bye. Bye.
Ciao, thank you.